Today's Technology Idea Exchange is presented by the 2026 Nexus XP People's Choice Award winner, Ginkgo Bioworks. The Nexus XP People's Choice Award is voted for by the conference attendees and recognizes the best integration showcase presented at SLAS 2026, highlighting integration, impact, and collaboration. Leading today's discussion, The Road to Autonomous Labs, is Ginkgo Bioworks' co-founder and CEO, Jason Kelly. Jason will start things off with a presentation, and then we'll move forward into discussion and Q&A. So please feel free to put any questions in the chat or raise your hand if you have a question throughout the presentation. Today is really meant to be an interactive conversation as well as a learning experience. So I am going to kick things off to Jason for a bit of an introduction of himself, his background, and then we'll get things moving.
Awesome. Thank you, Gina. Yeah, and I'll just reinforce the comment that, yeah, please do feel free to interrupt and would love to chat with folks. And there'll be time also at the end for Q&A too, but in the middle is great. My background, I grew up in Florida, went to MIT for undergrad. I was a chemical engineer and biology major, and then did a PhD in bioengineering. And then after grad school, we started Ginkgo back in 2008. So we've always been focused as a company in trying to drive efficiency in the research work associated with biotechnology. So started the company in '08, bootstrap for 5 years. Then we did Y Combinator summer 14. We were the first biotech to do YC right when Sam Altman, now Mr. Famous, had taken over as the head of Y Combinator, and he thought the Silicon Valley model could apply to biotech and nuclear fission and materials companies. So we leaned in on that, basically got treated like a tech company. So we kind of have always had one foot in the biotech community and one foot in the tech community. Raised about 900 million as a private company, took the company public in 21, with a business model really of research partnerships on top of a bunch of proprietary technology. So grew the business that way. We do about 200 million. Last year we did about 200 million in revenue. We in the last 2 years, 2.5 years now, really have taken a lot of the technology that we had in-house and also started to offer it directly to customers with more of a life sciences tools business model. So think like a Thermo Fisher, basically. And so you can now buy reagents from us. You can buy the automation equipment I'll be talking about today. And we're really orienting all of this around this concept of kind of the tools associated with an autonomous lab. And we do run a really large autonomous lab here in Boston, which I'll mention in the talk. You should come and visit. And we had more than 500 people during SLAS come over and check it out because we're very close to the convention center. More than happy to host any of you at any time. My email will be at the end, and feel free to email me and come by. Okay, so that's just me, Gina. So I guess I'll just dive in on the talk. Does that sound good? All right.
Yeah,
Hang
that'd be
on.
great.
Okay. Let's see. Okay. Is that showing up full screen?
Yeah, it looks good.
Okay, great. So I'm going to talk a little bit about this idea of autonomous labs. I think this is getting a lot more sort of purchased lately certainly around the tech community. This is a hardcore automation crowd here with SLAS, and so I want to draw a little bit of a distinction from sort of traditional laboratory work cells and kind of get in the weeds a little bit on what I think is different about autonomous labs. And again, very happy to discuss and chat about this. We had two pieces of news in the first quarter that I think were relevant. One, we did a partnership with OpenAI, where GPT-5 actually ran our autonomous lab here in Boston, and we beat scientific state of the art on cell-free protein production by 40%. I'll talk about this a little bit more. For our purposes, just to kick this off, I'll mention this was like the same day OpenAI announced Codex, and they put up an X post about both, and we had about the same number of views as the Codex post. So I think there is actually a lot of interest in the application of AI to science, and we'll talk about that in a minute too. We also were lucky to announce in December that we were awarded a large contract, $47 million contract by the Department of Energy through the White House's Genesis mission to bring AI into the national labs. I had the chance to ribbon cut our first 18 robot autonomous lab up at Pacific Northwest National Lab with the Secretary of Energy, right? back in December, and then this new contract is for another 97 robots in a very large setup. And so really excited about that. And again, I think this is a sign of where things are headed, and why I wanted to kind of make this distinction of what is autonomy, and why is it different than traditional automation. So we're going to talk about that first. Then I want to dive in a little bit on what an autonomous lab looks like and how scientists, and we have scientists here at Ginkgo using our autonomous lab every day. What's that experience like? And then finally, in my view, if we automate all of the lab work of science, that's going to greatly grow the customer base for automation companies in the automation industry, which SLAS is all about. And so I think this is a real opportunity for all of us on this call. So, okay. What is autonomy? So this is my analogy I like on this one. So if you bear with me for a second, I'm going to give you an analogy from the transportation industry. On the y-axis, we have the amount of automation for a type, that you would have for a type of transportation. Okay. And then on the x-axis, we have the request flexibility. In other words, a scientist is asking, or scientist, a customer is asking that transportation system to deliver them to a wide variety of places or not. All right. So for a low request flexibility and a high amount of automation, that's a subway. Been to Boston. That's the red line up there, our T subway line. It's great. It is fully automated. You sit down and it is end-to-end automated. It just takes you away. You don't have to do anything. But you better want to go to one of the stops on the subway line because it's not going to take you to your front door. Down at the bottom of that y-axis, amount of automation being low and a high amount of flexibility, that's a car. So you have a human in the loop. You have your hands on the wheel, your feet on the pedals, and it'll get you right to your house or the grocery store. It'll take you wherever you want, but it is not automated. It is manually controlled by you. And that's more or less how the transportation ecosystem looked for the last 100 years. Unless you've been to San Francisco in the last 4 or 5 years and you've seen these guys driving around. These are Waymos. This is I swear to God, amazing experience if you try one. You hit the app, the car pulls up, you get in the back seat. It's like being on a subway. It is end-to-end automated. You do nothing, but it will take you wherever you want. It'll take you right to your house. And so you get the flexibility of a car, but you get the automation of a subway. And that's so surprising. That amount of automation is so surprising. We give it a new name. We call it autonomous. We say it's an autonomous car. All right. And here's the kicker. If you look at miles traveled in the United States, more than 99% of miles traveled by people is cars and trucks, not trains and subways. And that's because we need the flexibility. Okay. We to get where we want to go, we need flexibility. All right. And even in the most populous train countries, it's still about 70% cars and trucks. Same reason. All right. Okay. So now let's talk about the lab. Low request flexibility, high amount of automation. As people know on this call, we do have those. We call those automation work cells. And this is a robotic arm, sometimes on a rail, in the middle of a set of equipment. We have a whole number of great companies in the industry, Thermo, Hi-Res, Biosero, who make these types of devices. They're built custom for your application, and they are end-to-end automated. It's beautiful. We've bought many of them at Ginkgo over the years. And you have a robot. That robotic arm means that a scientist doesn't need to move the plates among the equipment. It means you can run your process start to finish overnight without humans in the loop. The issue, of course, is you pretty much have to have it do the same experiments it was doing yesterday. You can't easily reprogram it every morning to do something different. It's quite inflexible. Drop down that automation axis there on the y-axis and go across on request flexibility. We have low automation, high flexibility of requests in the lab. It's called the lab bench. You stand in front of it, and I did my PhD at MIT. I lived this experience. You can do any experiment you want. You grab the pipettes, you grab whatever reagents and kits you want from the shelf. You move samples to any piece of equipment in the manual lab that you're standing in, and you can do an experiment you just read about yesterday in a paper if you have all the required equipment and reagents. And so you have a huge amount of flexibility, but you as a human are in the middle, providing sort of the manual labor that allows for that flexibility of work. All right. And so the reason I give that example is because if you look at the spending across sort of large pharma companies or Others, you'll see there is, at a place like a Merck or something, a $3 billion a year research budget, of which only a very small fraction is going to the automation work cells. The overwhelming majority is going to millions of square feet of manual lab benches, benchtop equipment, EHS to support all of that, the whole shebang. And so at the moment, again, it's not like we don't know, just like in transportation, it's not like we didn't know about rails and subways. It's not like we don't know about work cells in pharma and science academic institutions and so on. It's that they don't provide the needed flexibility for scientists to do their jobs, except for in niche areas, high throughput screening and so on, things where you're repeating experiments, diagnostics, so forth. And so what we're trying to build at Ginkgo is what we call an autonomous lab, and it's meant to give you the automation of a work cell, but the flexibility of a lab bench. All right, and so that's why I wanted to distinguish, again, this idea of autonomy and what is an autonomous lab. That is really how I'm defining it. I'm trying to solve that problem of flexibility and automation at the same time, like has been done with autonomous cars. Okay, so the key technical challenge for those of us trying to do this is how do you get that same flexibility that you would get at the bench, right? That flexibility is typically the enemy of automation. Okay, so I'm going to dig in now on what that looks like. But maybe before I do that, I'm happy to take a pause on, does that framing make sense to people in terms of the idea of an autonomous lab, like an autonomous car, trying to solve that problem of giving you the flexibility that usually requires a human in the loop?
Hi, this is Manoj Ramji.
Amen.
You probably looked at LinkedIn in my profile, but so I just
Yeah,
background, so you know where I come from and
yeah,
the direction I'm coming from. I've worked in automation for a very long time, over 30 years, and I worked as a principal biologist for a company called Cyclofluidic,
yep,
and we built a platform that did compound synthesis, analysis of that compound, quantitation, bioassay, all in one single platform, and then
yep.
put it into a machine learning algorithm. And using a subset of compounds on a deck, it decided, chasing potency or selectivity or whatever, to make the next compound autonomously.
Very cool.
And we've written papers in JMed Chemist and the like. And this was a one platform that did chemistry, analysis, bioanalysis, machine learning, and the next compound. So I would say within 72 hours, we could hone in on a compound from a hit to get a
Yeah.
lead. So that encapsulated chemistry, analysis, and biology. So at the moment, from what you've discussed, can you give us an indication of what you're encapsulating? Are you encapsulating biology? Are you
Yeah.
encapsulating analysis? Are you encapsulating chemistry?
Yeah, that's a great question. So I would put for my definition, this was just me, by the way, of an autonomous lab, I would put the analysis outside of that. Okay, and we'll come to a minute later about AI, what I'll call AI scientists, right? Like the project we did with OpenAI, GPT-5 ordered experiments from our autonomous lab. The lab, in this case, it was 100 384 well plates per round of experiments. It ran the experiments designed by the model. The data went back to the model, but no analysis was done. The analysis was done over here by GPT-5. So it called various data analysis packages and so on, had access to a computer and programming environment and all that sort of stuff. And so it did the analysis. And I would say that's sort of the AI scientist using the autonomous lab. But the autonomous lab's job, and my analogy from a Waymo here would be like when you're in the back seat of a Waymo, you tell it where to go, right? The human directs it, but it's still an autonomous car, right? So the definition of autonomy in the physical world here, again, I'm saying is sort of getting people out of the loop in these high flexibility environments. That's my definition of an autonomous lab. I'm not trying to add in the extra element of the who is interpreting the data and designing the experiments. I again, for my purposes, my ontology here, I'm putting that into the AI scientist category. Okay, so that's sort of point number one on your question about like analysis. To your point about like what kind of lab work. So our mental model now, I'll now dig in on this second section, unless anyone else has a burning question. In the second section here, Manoj, I'll talk about sort of how we think about integrating equipment. But the short answer is anything that can receive SBS format plates, I think we can ultimately work with. Chemistry automation is sort of a, for synthesis, is its own sort of puzzle that a lot of people have worked on over the years. There's a lot of good companies working on that now, from ChemSpeed to Crystal Pi to, I don't know, there's 5 or 6 that are again trying to solve that problem in the general case. Merck KGaA has a pretty neat setup up in Billerica. So I do think that's still a problem that could use some work. But yes, we'd happily integrate any device that kind of sends and receives SBS plates. But again, I'll get into that a little more in this next section.
Okay.
Tony, I saw you unmuted, so if you did, you want to ask a question?
No, it's cool. Thanks.
Okay, no problem. Okay, then I guess I'll keep going, and then we'll have I'll stop again maybe after this section to take more questions, or again, feel free to just interrupt. Okay, so not like I mentioned, Autonomous Lab has to allow a scientist to do the same work they would do in a traditional manual biotechnology lab. So I think this is one of the key things people get mixed up on. They're sort of initially, you're like, hey, I'm talking about automation, so I naturally should comp this thing to the work cell, to the subway. But I would really encourage you not to do that. I would encourage you to try to comp it to the lab benches. Because again, there is an enormous amount of spending and effort going against all of these manual lab benches every year. Many, many tens of billions of dollars being spent on lab benches in both academia and the biopharma sector, because they do deliver value as they operate today. So how do they operate today? Let's talk about what's going on. And by the way, if you've seen me on LinkedIn, I'm kind of like an influencer now. Do a lot of these videos, embarrass my 13-year-old daughter. Here's me at the lab bench, just showing people some of the basics of what you do with manual lab work. And so the 3 things I think are critical. First is and this is oriented a little more towards biotechnology in particular, so more biosciences to Manoj's point. One, you pipette liquids, right? So you are serving as a complicated liquid handling robot, right? Which means that you're able to eyeball things, you're able to handle viscous liquids, you're sure when the pipette tip clears. There's a lot of things you're quite good at as a bench scientist in terms of being able to move a diverse array of liquid types well on a bench. Second, you move samples between different pieces of laboratory equipment. So you can, using your hands, get a sample, and then using your legs and feet, walk across the laboratory you're in and deliver that sample to any other device in the lab. Okay, you're not like frozen in place and can only reach the 5 things at your bench. You can actually walk anywhere you want and go connect protocols that may use 5 or 6 different devices within a lab that might contain 50 or 100 devices. And then finally, you can input the settings on all those different benchtop devices. So you have, you might run the PCR machine this way, you have your particular settings for the LCMS, whatever it might be. You're able to tune those different devices for the particulars of your experiment. And so all that's under your control as the scientist. I think if we want to replace that manual lab, that car, with an autonomous lab, with a Waymo, we need to do these things. The first 3 I just told you: liquid handling, material transport, parameterized control. But very importantly, you have to do that across the 50+ devices that would be typical in a manual lab. You can't just connect 5. Okay, because if you walk into a lab at Merck or the MIT biology department, you don't just see 5 devices in the lab. You see 20, 50, if it's a big lab, 100 devices. You need to support parallel work. It's not the case that only one scientist uses that lab at a time. 10 or 100 scientists may share a laboratory environment. And then finally, it needs to be as easy to use as the lab bench. So, you don't have to program, for example, in order to do your experiments at the lab bench. It needs to be straightforward for the users. So this is a really hard, right? Like if I were to frame the problem out, I'd say the first three are reliably done by work cells today. There's a whole beautiful set of liquid handling devices out there from the automation industry. Folks are probably on the call today for all different types of liquid classes, different volumes, acoustic handling, positive displacement tips, all the things, right? So there's a lot of great, reliable liquid handling that's been automated. There's material transport to devices. The arm can move plates around pretty well, better every year, in fact, with things like feedback from images and stuff like that. And then there is parameterized control of devices. So all your kind of automation integrators have done the work of connecting those devices into their system. Where it starts to fall off pretty quick is when you try to put a lot of devices together. There's been a few instances of this and sort of like old sorry tales from the industry of people who've tried to do these huge setups and it just kind of never works out right. And so I think that has not been done in a particularly scalable way once you get to huge number of devices in a single setup. Supporting parallel work, I'm not even sure many people have tried this, where you would have 30 different scientists submitting jobs on a given day. I think the assumption has been the systems just can't handle that. And then these have certainly not been easy. Typically, the way a scientist engages with a work cell is they talk to an automation engineer and they tell the automation engineer what they want done. And then the automation engineer translates their intent into code on, whether it's a graphical programming language or otherwise on a work cell. And so it's not particularly easy for the scientists themselves to use it. It's, easy enough for an automation engineer, but that's a translation layer. And so those are the things you really have to work on if you want to solve the autonomous lab problem. And again, I would say the principal distinction is the work cells are being designed to be a subway, right? Like they are being designed against a particular high throughput workflow that a customer wants, which means you can kind of do a lot of things. You don't have to solve problems 4, 5, and 6. Why do I need 50 scientists to use this if it's going to be a high throughput screening facility run by 4 automation engineers? They're just the 4 people that need to use it. It doesn't need to be easy to use. They can be well trained and so forth. So there's sort of a set of constraints once you're committed to making a subway that I think lead to why work cells look the way they do. Autonomous labs are not designed around a protocol. They're designed around the equipment that you want to put together into a system. And so Ginkgo's technology, and this was actually technology we acquired from a company called Zymergen originally. So this is now 10 years in the making. This is the newest generation of our reconfigurable automation carts. And what we make is the cart, which is that thing on the wheels there with the box and the HEPA filter on top. It's under positive pressure. And inside of it is a third-party device. So in that case, there's a centrifuge, and we have a 6-axis robotic arm and a piece of magnet motion track in the front. And the way this works is you can put them together Lego block style. So you tell me I need these 10 pieces of equipment. I say, great. I'll send you 10 racks with those 10 pieces of equipment, and you will Lego block them into a big setup. And then once they're all put together, this is sort of what it looks like. This is actually one of the protocols that from the OpenAI project where we were sending samples. So here's a plate getting put onto a puck on that Magnemotion track. It's now going to move, and it can be delivered, remember, to any of the devices that are on that rack system that are connected. So in this case, it's getting sent to that centrifuge. And the centrifuge will do its step, and when it finishes, that arm would pick it up and send it, in this case, to an echo, right? And for the OpenAI project, each one of the wells in that echo plate, the actual design of the particular hit pick pattern was coming from the GPT-5's particular set of reagents that it wanted to put together. This is a Bravo liquid handler now. So now we're going to do some stamping where we're adding the DNA into the cell-free protein synthesis reaction. But again, from the standpoint of the rack system, this is one particular workflow that is flowing through the system. And so, on the other side of this, this plate is going to get sent over to a shaker and then ultimately onto an analytical device for basically measuring the amount of protein that got produced by that particular set of reaction conditions. And then that data flows out of the system in a nice clean format, because again, all this stuff is all fully automated. So you have sort of an end-to-end track of the whole protocol. You have any errors recorded along the way, so those can be also provided. In this case, back to the model. So if there was like an error in the hit pick or something from the echo, you could tell what actually ended up in that well. And then finally, the model can do what it wants and design the next set of experiments in this case. So I want to just show kind of what that looks like. That's just one protocol running. The key idea here is you can interleave many protocols. So each row on this chart, this is a screen grab from our scheduler one day here at Ginkgo. We are fortunate. We do research projects for a number of large pharma companies, Merck, Pfizer, Novo Nordisk, Bayer Crop Science, others, where our scientists use our automation to do research in partnership with these companies. So we're having our own scientists use this thing every day. They're a little bit like the Waymo engineers 5 years ago in the front seat of the Waymo with their hands like an inch from the wheel, grabbing it if it goes in a mailbox or something. Our scientists are putting real scientific variable work on the system every day. And so each row here is one of those devices you saw, so one of the racks on the system. The orange line is time, like to now, and the x-axis is the future. And so what you're seeing is different color protocols sharing the equipment. And of course, you can't use the same piece of equipment at the same time. And so you see how the colors sort of alternate as different protocols have been interleaved together as they were submitted by scientists. And so we have a bunch of different variety of different protocols here on the left. And then you can see requested by, you can actually see a bunch of different names of scientists who are actually putting in these protocols. All right. Again, so we're trying to avoid that thing where everyone's being bottlenecked through one or two automation engineers, but rather the scientists are able to submit their protocols directly to the system every morning and then have those get interleaved together and run throughout the day. They can start small and grow big. So for people that are building a work cell today, like they're building a subway, you can use the system as a work cell. It is able to just be run over and over again. We have some customers that do that. But then it serves as a base to ultimately grow into a bigger system. So even here at Ginkgo, we originally had 8 racks, I think, doing NGS prep. Like the preparatory protocols for next-gen sequencing, but that now is 52 racks. And as of, I think by the end of this week, we'll be up to 70. The rest are in, but they're just getting added to a new line on the system. And by May, we want to be at 100. So that sort of putting many devices together, we've run that experiment, and that looks good with the choices we've made on the physical hardware. That's like, for example, every device having an arm. That's so that you can run many devices in parallel, right? Otherwise, that one arm, you put one arm in the middle of 50 devices and you have a major problem in terms of bottlenecking. And then supporting parallel work, we are actively running the experiment of what it's like to be interleaving everybody's science together. Things break all the time. We're fixing them all the time, but it's actually working pretty nicely. And it does run 24/7. So I love logging on my computer at home and seeing what 20 different protocols are running on the system right now at 11:30 at night. Last thing I'll mention is it as easy to use for scientists as the lab bench. I think here we're getting a real benefit from what's going on in the AI space. So you have companies like Potato and Chechuan, Elnora, Briefly Bio, all these people that are working on the problem of how do I take what a scientist wants to do? Like imagine they were talking to a technician about an experiment they want to run. They were the PI of a academic lab or the group leader for a pharma drug discovery group, and they tell one of their technicians, "Hey, I want this. Here's the kind. I just read about this experiment. Here's how what I think are some of the things to watch out for. Let's do it like this. And could you kind of try it over the next couple of days and come back to me with some data?" You would like a similar experience talking to the autonomous lab. And that's something that would have been just absolutely crazy a couple of years ago, but now is getting increasingly feasible to turn human language into a reliable automation code to operate the robotics. And so I do think that's ultimately going to be how this stuff works. These are just some pictures from the lab. Like I said, we had about 500 people come through during SLAS. You can just go to this link, calendly.com, Ginkgo Bio, tour-Ginkgo, and sign up. We do tours every week. You can just grab a spot if you're through Boston anytime and come see it. We're like 10 minutes from the airport, so you can tack us on a visit very easily. So I'm going to pause there for a second. That's a little bit more detail about sort of our theory on automation and sort of how we approach the hardware and the problems we're trying to solve on the software layer, and this idea of sort of like AI assisted coding as coming together to solve some of the problems I think have kept automation from becoming flexible enough to attack the bench. Next, I'm going to talk about a few things I think just for the industry-wide kind of conversation to think about, but that's a little bit more on our technical choices. So maybe I'll pause for a minute and see if anyone has any questions.
Hi there. Yeah, that's really interesting. Um, so I'm Steve Truman from
Yeah.
Ventera Bio. I also run the Agritech TIG. So it's nice to hear you mention some doing some crop science stuff.
Yeah.
And one of the things several of our members get frustrated with is the I guess protocol languages of integrating different vendors' instruments. So what you're saying here is that the AI can actually basically translate and be the middle person in that language translation piece.
I do think that will, yeah. So here's what I'll say where it's at today. Okay. So where it's at today is it can certainly write a draft protocol for you in basically, I think, certainly we're doing it with our partner language, but I think you can do it on you could ask it to write code, I think, in anybody's. The question will be, is it going to be good? Right.
Yeah,
Like, is there going to be some errors? You're going to spend as much time debugging it as you would have spent writing it in the first place. And that's where I think companies like the ones I just listed there are trying to take the edges off the places where the models might get it wrong, because there's a whole bunch of not just, sure, the code compiles, but then when you run it on the robots, is it going to do something stupid in the physical
yeah,
world?
yeah.
Well, how do you check for that? Right. And so that requires sort of another level of sort of software checking and other things and so forth for these models in order to kind of harness them into being better kind of virtual automation engineers to some degree. Does that make sense, Steve? And but will it,
Yeah.
like, I mean, I personally, I'm a big fan of where this stuff is going. Because if you look at what's happened on the coding side, you absolutely can do that. You can be like, take this Python code and translate it to this other language. And here's the series of checks I want to run for you, the unit tests, in order for you to confirm that you did a good job with the translation, and it will do that. And so I don't see why we shouldn't be able to do that too. But the checking in our world is a little bit more complicated than in the world of pure software. Does that make
Yeah,
sense?
yeah, absolutely. I'm just sort of wondering whether it's easier um, to to get an AI translation piece than it is to get the vendors to make compatible
Oh,
software.
probably. Yeah. I would say so. Yes, I would count on the software being able to do it for you. Yeah.
Cool, thanks.
Yeah. Cheryl, I saw you raise your hand.
Oh, there you go.
Oh, or Gina, or
Got it, Chase.
whomever. Yeah. Okay.
No, I was gonna say Cheryl too. There we go.
Fascinating. My question's about the parallelization. So
Yeah.
so if you've got a track, how do you parallelize? Or do you move components in and out during an experiment?
Yeah, good question. So you notice how there's like it's a little, unfortunately, I should maybe get like better aerial view or something. But you see how there's like little loops there. So you basically can have like cutovers. Where if you wanted to, like, if you have a puck and you want to move it out of the way, you can put it into like a cutover between the loops. You're not always like kind of linearly moving around the loop. You can cut through. The other point is it's really we don't leave the job of the transport system is bring a plate to the arm. The arm takes the plate, and then you get the heck out of there. So you're not like lingering while whatever is happening on a particular device. You're like point to point transport and then go to the parking lot.
Yeah.
Okay. And so in general, you're really just avoiding each other as you move quickly. And then within 20 seconds, you're off the track. So you don't have these sort of like long pauses where like something would block the road for very long. It's not going to block it for more than 20 seconds,
Yeah.
even on a big setup. Does that make sense?
Kind of. So you're saying that people will come and move or no?
No. So you remember how like the that I showed in the video, the puck moving along the
Yeah.
track? Okay. So we can software control that. So here comes a puck.
Okay.
It comes
Yeah.
in front of the centrifuge. The
Right.
arm picks up the
Yep.
plate, puts it on the centrifuge.
Yep.
Now that little black puck, which something can't go by it is blocking the track in
Oh, I
that
see. Okay.
it's done. It can get the heck out of there. It doesn't need to wait around for the centrifuge to spin
Right.
for 10 minutes. It just leaves and gets out of the way. right? And then that means the track is now open for anybody else to come by.
Yeah. And so the track can access all available pieces of equipment somehow.
Correct. Yeah. The track goes, yeah, it's embedded in the cart I showed you. There's a piece of track inside every cart. And so when you saw the little plate come down the rail in the video, he was moving inside of every cart.
Yeah.
And so it could go in front of any piece of equipment on the system, just depending on what the software wants it to go. And if it pulled up behind another puck, because that one was loading onto the centrifuge, it would just wait a sec while that thing gets unloaded, and then they both move off. Right. But it doesn't need to wait for very long because you're only there for the time it takes to transfer the plate off the puck.
So what made you choose the sort of on deck as opposed to maybe above or something like that?
Sorry, on deck.
Well, you know, you're kind of running through the instruments. I can imagine a different approach where you'd run it above and drop the plates down. Is there any rationale or you just chose that?
No, it's a good question. Yeah, and you see some like semiconductor fabs do a lot of the like above transport. A couple reasons. It keeps it inside the box. So for like contamination and things like that, we have positive pressure. So we do a lot of work with like mammalian cells, for example, and we have customers that have been running the system for 3 years with no contamination events with mammalian cell work. So that's one of the advantages. The rails are in the cart, so they line up nicely, so you don't get issues there. I think I'm sure there's another version of it where you could have put it on top, but it just seems to work well for us.
Cool. Thanks. Appreciate it.
Other questions from folks? Paul.
Hey Jason, hang on, I'll find my video there. Hopefully that's going to work. I am live. Entirely self-centered question here.
Do you want to introduce yourself, Paul, just for people?
Oh yeah, so I'm Paul Marshall. I'm CEO, founder of Rapid Fluidics. We design and make microfluidic systems. So obviously I've got an entirely self-centered question. Where do you see microfluidics sitting in the development of autonomous labs?
Okay, so I think this is a good topic. So, and I'll talk about this in the next section a little bit. So my macro thesis on all this is, once you get something end-to-end automated, particularly in biological sciences, you can start to really drive the cost down through a whole bunch of other means that aren't just integrated automation. And the best example of this is what happened with DNA sequencing. Right, which like a company like HiRes originated because of the Human Genome Project, right? Like the original design of high throughput sequencing was integrated automation moving among the manual steps of doing sequencing back then, right? And the semi-manual, right? And then once you kind of had it, you're like, okay, well now we know the whole thing. Where can we start to take costs up, blah, 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 and you start to just invent. And the very natural place to go with biology, because like semiconductors, it's a miniaturized discipline, is to make everything smaller, right? I mean, you save on reagents, you save on everything, you save on space, like it's of course, right? And so I think that's a very natural flow. The issue for us in the industry is there's not a lot of things like sequencing that are the same protocol with like infinite demand.
Yeah.
Okay. And so what we got to figure out, we got to take the variable work, get it end-to-end automated. That's what I'm trying to do here with the autonomous labs. And then once we have a paradigm for that, the next question becomes, okay, how do we start to miniaturize variable work? Okay. And I think, but I think it's first step is get off the bench. Second step then is make everything smaller. Now, in the meantime, if there's any individual, like if there's a microfluidic version of a benchtop device, there's no reason not to integrate that into an autonomous lab as a unit operation. But the long game, I think, is there'll be a version of what you see on these pictures 5 years from now that the whole thing is only this big. Because everything's just moving around and you've kind of reduced a bunch of these various biological unit operations to microfluidic unit operations. But I personally think the path to that goes through first killing the bench. And then we can start to do it, just like what happened in sequencing.
Yeah, that's definitely the way forward. I'm obviously kind of focused on the ability to create individual microfluidic devices bespoke components instantly. And I kind of see that autonomy of the manufacturing line sitting in line in parallel to the science lab. So you're running the engineering with the science. The whole thing is driven by an AI model, so it can create components that it puts into the autonomous lab. And I think that's possibly that's the future I'm looking for. So but we've got to get there. We're not there yet by a long shot.
Agree. Yeah, here.
Cool. Thanks.
Other questions on the sort of engineering or technical design before I move on? Okay. All right. Okay. Automating all of the lab work of science is going to both make our customers' businesses better and also grow the automation industry. So again, I'm just going to harp on this a little bit because my point earlier about like 99% of the miles are driven by cars and 99% of the research spending is at the lab bench. The value prop to a head of R&D today to kill all their lab benches is one, massive overhead cost savings. I mean, this stuff just eats money every day of the week by just sitting there, right? Even if no scientist walks in your lab that day, it costs you a fortune just to have it sitting there, regulated, fed well, temperature controlled, air changes, all the things. Second, the research productivity of your human scientists is limited. For starters, they only work 40 hours a week. Right? Again, the autonomous labs are running 24/7. So you could get a tripling of their productivity just in time because they can now order experiments overnight and on the weekends. It's also much more space efficient than manual labs, about threefold reduction in lab space needed for the same amount of equipment by going to an integrated automation autonomous lab. So I think there's about a tenfold improvement overall in research productivity just in time and space improvements compared to a manual lab bench. The other thing is there's a lot of interest right now around that AI scientist topic I talked about. You just mentioned there, Rich, too, around the lab in a loop, where the scientist, like we did with OpenAI, is actually an AI model and it's kind of running experiments all the time. I think as you see more interest in that from heads of R&D, I think that's another reason to bring in these autonomous labs. But the big kicker is, you're spending a couple $1 billion on this and you're only spending less than 100 million a year, if that, well less for many cases on work cells. I think those numbers should flip. I think the average pharma company should be spending $1 billion or $2 billion on automation, not the other way around. The market for science-based companies, I think, will be much bigger if we manage to kill the lab bench. So today, if you look at a company like Thermo, 80% of their revenues are coming derivative from the biopharma industry because biopharma is sort of the physical science-based industry. It's the industry that is taking regular scientific risk, like, can we cure Alzheimer's? Like, who knows? It might be 50 years away. It might be 5 years away. They're taking real scientific risk to deliver new products every year. Okay, most other industries don't look like that, right? Like even say the chemical industry, they're not taking flyers on. They did back in the 30s and 40s, but nowadays it's a much more mature industry. You're not seeing just like wild swings with scientific risk. I think outside of pharma today, I think there could be many more industries where physical science-based risk was being taken regularly if it just wasn't so overwhelmingly expensive to do work at lab benches. Right now, pharma is really the only industry that's got the kind of feedback loop of value to keep the lights on Ignite $3 billion a year at Merck or something to try and do open-ended science. You are seeing a lot of action, I think, right now in Silicon Valley. Companies like Periodic Labs raised $300 million out here in Boston. A company called Lila raised $500 million. Anthropic just bought a stealth biotech-ish company. I think this is a little more on like the clinical side, but still like interesting signal. So I do think there is a little bit of a wave here around, hey, can we take a new approach in the era of AI where we combine AI and robotics to do science in a new way that could maybe open up a whole bunch of new markets even beyond pharmaceuticals to this type of approach. I also think there's an awesome value proposition for many other types of people that are at SLAS, like the automation engineers. This is our moment, right? If we can get automation to be as flexible at the bench, we can get out of the basement where the work cells are relegated to today. So I really think this is like a great opportunity for the industry. I would love to see more people lean in on this messaging, building devices, building integrated systems, building software, and killing the bench. I really think we should all try to kill the bench. Okay, I already kind of brought this up earlier, so I won't belabor it, but AI scientists are different than autonomous labs. I think people often are putting all this together, and I do think they're really different from each other. I think a human scientist will be augmented by an AI scientist. In some cases, the AI scientist will do what the human scientist would normally have done, data analysis and planning. I think those are going to be scoped down to more sort of like the more design of experiment, more a little bit more of the repetitive work rather than totally open-ended research, although we'll see. I think, but the autonomous lab part is just great for scientists, in my opinion. I think this is a way for them to get to do more experiments per dollar, increase the ROI of what's in their head. It's just awesome. And so they are two different things. We did do this project with OpenAI where we had the OpenAI GPT-5 actually run the lab. This is what that looked like. We had obviously our part, the racks, but what GPT-5 did was it would design a set of experiments. We have what we call it's called like a pedantic model. It's basically a set of rules in a structured code language that said you can give us samples, GPT-5, like you can design experiments, but we have a certain set of rules about this 384 well plate. First off, we're going to use these two columns for controls because we want to publish this and we are going to need well-controlled data in order for people to believe it. We want you to do 4 replicates of each one of your particular designs. And in this case, what we were asking the model to do was increase the amount of protein you got out of a cell-free protein synthesis reaction per dollar of reagents that went into the reaction. And you were allowed to change the reagents. You could take reagents out, you could order new reagents from the thermo catalog, whatever, right? Like you could choose GPT-5 what reagents to put in addition to an E. coli cell-free extract. And so what reagents do you pick to improve protein per dollar? That was like the question put to the model. But we did say, hey, you got to follow these rules. Another rule in the pedantic object was the volume of liquid you were allowed to put in a well. If you put too much liquid in the well, it's going to overflow. So we had those set of rules. But then within that, the experimental wells on the plate, it was up to GPT-5 what reagents it would put in. And if it just told us, hey, fill the well with water, as long as it was below the volume, that was the rule, we would have filled the well with water. Okay, so we did not put our human fingers on, are you making good choices about what reagents to do? On the far right graph, excuse me, you can see the basically the dollar per gram of protein being made falling over time. The dotted line in the middle is state of the art. That's what had been shown in Mike Jewett's lab at Stanford. I'll note we were kind of varying a few different. This is the first time anybody's done this, so we were kind of changing a few things at once. But in the first 3 rounds of the experiment, in each round, it had 100 384 well plates to design. We did not give the model access to any tools. So in other words, it did not have access to the internet. It did not have the ability to program data analysis. It did not get to read Mike's paper and know what the state of the art was. It just had to try from its knowledge, because it already has been trained on a lot of the internet. It had to take its best swing at setting reaction conditions. So the good thing is, over a couple of rounds there, it actually was able to get data back and improve itself just inside the model. But then on step 4 there, we gave it access to basically everything a scientist would have access to. The paper from Mike's lab, programming tools, anything it wanted. And that's when we beat state of the art. The next round, we actually did better than what they had done. And in 2 more rounds, it did keep improving, ultimately beating state of the art by 40%. And we can download our paper there, or our preprint anyway, on bioRxiv at that link. Okay. So I'm not going to say too much more about that. I will say I do hear from scientists, like, and one of the things that frequently gets asked about when it comes to autonomous labs and even just AI generally is sort of what's this going to do to jobs and so forth, and scientist jobs in particular. This is an old article, old advertisement from like 1952, IBM ad for IBM electronic calculator. Speeds through thousands of intricate computations so quickly that on many complex problems, it's like having 150 extra engineers. And then here's all the engineers with their slide rules. Because pre-IBM, we did computation manually. And so I think a reasonable person could have said, wow, I mean, engineer jobs, the people holding those slide rules, are going to fall off a cliff on the other side of electronic calculators and computers coming from IBM. Now, of course, the exact opposite happened, right? We had a massive explosion in the number of people with these jobs. And by the way, the people who had the jobs right at that time, their value skyrocketed because the ROI, like the return on investment for what they could think in their heads, increased massively after we automated computation. Because up until then, well, however smart they were, to actually go through the math of doing the things they wanted to do, you had to pull out a bunch of slide rules and have a bunch of people do the work manually. And so that change, I think, is what we want to have happen in science. We want to put away the pipettes, okay? If we want to unlock our scientists and get them getting the full ROI, the full return on investment of every great idea they have, the cost to turn their idea into the data that proves whether that idea was right or wrong needs to drop. And if we do that, I think we'll have a vast increase in the number of scientists, both professionally and I think even in the amateur kind of science world, just like we did with amateur computer programming, right? My kids program computers now. I mean, that in 1950 would have seemed absurd. I do think we could have a similar transformation if we make autonomous labs inexpensive over time, where you could have, generations of a future generation of kids being able to just order experiments. And so we've even, we at Ginkgo, using our lab here, offer it at cloud.ginkgo.bio. You can order an experiment for $39, where we'll just run something on the lab that you design. So that's sort of the beginnings of that way of thinking about things. That's it. So that's my email up there. We have, I think, 5 minutes for a few more questions, but if we don't get to something you wanted to ask or you don't want to ask it here on the call, definitely feel free to email me. And again, I'll encourage people. We're just 10 minutes away from the airport in Boston. If you want to come and visit, you can also just email me and I can get you set up with that too.
Great, Jason, I can kick things off. There is a question in the chat. So do you realistically see Ginkgo reaching profitability by 2026 as a result of scaling its autonomous lab strategy, or do you expect the transition phase and investment cycle to delay meaningful profitability beyond that horizon?
Yeah, so on our last earnings call, we talked about this a little bit. So I guided to a cash burn for the year. So we are planning to burn cash this year as we grow into this space. Now we're fortunate, we ended last year with around $400 million in the bank. We have no debt. Our cash burn is dramatically lower than it was a couple of years ago. So we have multiple years of runway in front of us, even at that burn rate. But we are seeing a good ramp in revenues from automation, our reagents business, and the cloud lab, these types of services we're putting on top of the system as we move more to a life science tools company. So I feel good about it, but no, we're not. We're intending to invest into growth this year in 2026.
Okay.
All right. Awesome. Well, Gina, I appreciate you getting everybody together. This was a lot. Is there anything else in the chat? No,
No, it was just a thank you.
Okay. All right. Perfect. Okay. Well, thanks everybody for the time. And again, my email's right there. We're always happy to talk to folks. And if you want to have one of these labs for yourself, we're happy to build it for you. If you want to try ours as sort of a cloud or as a demo, we're happy to run your protocols on. Like I said, we have 70 racks put together here and soon to be 100. So we have a lot of different equipment. If you're a vendor and you want us to integrate, like a device vendor, and you want us to integrate your equipment, we're happy to do that. We put new equipment on all the time. It takes about a month. And so if you think yours is a particularly good fit for the autonomous lab, also email me. Yeah, super excited. And I think this is a good trend for the industry, the excitement around autonomous labs. So happy to be a part of it. And thanks for all your time.